Now we go in elementary properties of group. These are the theorems in group. Group ko theorem ho yo. First theorem is the identity element in a group is unique. The identity element in a group is unique. Group मा भएको identity element चाहिँ के हुन्छ युनिक हुन्छ. कुनै पनि एउटा एलिमेन्ट को एउटा भन्दा बढी आइडेन्टिटी एलिमेन्ट हुन सक्दैन एउटा ग्रुप. त्यसको हामी प्रुफ गर्छौं. Proof of this theorem 1. Proof. Let E be the identity element. E be the identity element in Z comma not. We suppose that E be the identity element. E be the identity element in Z comma not. And E dash be the other identity element. It has be the other identity element. We suppose here two identity elements, and so these two both identity elements are same. Therefore, E not E dash equals to E dash not E equals to E dash, we can say, since E is the identity element. Since E is the identity element. Again, therefore, E dash not E equals to E not E dash equals to E, since E dash is the identity element. E dash is the identity element. Therefore, E equals to E dash belongs to Z. E equals to E dash belongs to Z. हामीले एउटा E लाई आइडेन्टिटी एलिमेन्ट भन्यौं, फेरि E dash लाई पनि अर्को आइडेन्टिटी एलिमेन्ट भन्यौं. E र E dash लाई अपरेट गर्दाखेरि E dash र E लाई अपरेट गर्दाखेरि E dash आयो. फेरि E dash र E लाई र E र E dash लाई अपरेट गर्दा E आयो. भनेपछि दुवै अपरेसनबाट के आयो? इक्वल आयो. E dash equals to E. Therefore, E dash equals to E belongs to Z. So, the identity element in a group is unique. In a group is unique. It is proved. This is proved. Now we are in second theorem, theorem number 2. We are in elementary properties of group. For this, we prove theorem number 2. Theorem number 2 is every element in a group Z comma not has a unique inverse. Every element in a group Z comma not has a unique inverse. We prove it. Proof. अघिको जस्तै हो यो पनि, अगाडिको जस्तै. Let A inverse belongs to Z be an inverse element of A. Therefore, A not A inverse equals to A inverse not A equals to E. Again, let A dash belongs to Z be another inverse element of A. Therefore, A not A dash equals to A dash not A equals to E. Now, we suppose A inverse and A dash are two inverse elements of element A belongs to Z. अब हामी A inverse र A dash लाई के देखाउँछौं? सेम देखाउँछौं. त्यो देखायो भने हाम्रो यो प्रुफ भइहाल्यो. युनिक इन्भर्स भन्ने कुरा प्रुफ हुन्छ. Now, A dash or A inverse we can take. A inverse equals to E not A inverse, we can say. A inverse equals to E not A inverse. And E means A not A dash not A inverse. Now we can say here A not A dash not A inverse. Now we can say here A not A dash not A not A inverse. This is associative law. Associative law. Now we can say A dash not A not A inverse is E equals to A dash not E is A dash. since E is the identity element, E is the identity element. Now what we proved here, A inverse equals to A dash. Therefore, conclusion I write here. Therefore, A inverse equals to A dash belongs to Z. So every element in a group has unique inverse. So every element in a group has its unique inverse. Unique inverse. It is proved. This is the proof of this theorem. Theorem 3, it is cancellation law. If A, B, C belongs to Z, not, and A not B equals to A not C, then A we can cancel and we can say that is B equals to C. And if B not A equals to C not A, then also here we can cancel A and A. We have to prove B equals to C. These two things we need to prove in this theorem. This theorem is known as cancellation law as well. Proof. Let A, B, C belongs to Z naught, and let A inverse belongs to Z be an inverse element of A. Inverse element of A. We have to suppose A inverse belongs to Z be an inverse element of A. Therefore, A not A inverse equals to A inverse not A equals to E belongs to Z. E is the identity element, belongs to Z. Now, we have A not B equals to A not C. A not B equals to A not C. We have to prove B equals to C. So we need to remove this A. We need to remove this A. To remove this A, what we do here, we have to operate in both the sides by A inverse. We have to operate both the sides by A inverse in left. Because A is here in left. A कहाँ छ यहाँ लेफ्टमा छ. A लेफ्टमा भएको हुनाले हामीले यो A लाई हटाउनको लागि A इन्भर्स के गर्न सक्छौं, दुवैतिर अपरेट गर्न सक्छौं. Now, operating both sides by A inverse on left. Operating both sides by A inverse on left. Left भनेको यो साइडमा हामी अपरेट गर्छौं. Not in right side, we have to operate in left side. Therefore, A inverse not A not B equals to A inverse not A not C, or A inverse not A not B equals to A inverse not A not C. This is associative law. We have used here associative law. Since we use associative law, now A inverse not A means E. A inverse not A is equals to E, or E not B equals to E not C, or E not B is, therefore E not B is B equals to, and E not C is C. Since E is an identity element, E is an identity element. B equals to C. We prove B equals to C. Similarly, if B not C equals to, if B not A equals to C not A, B not A equals to C not A, then we can show B equals to C. It is proved. जस्तो कस्तो भनेदेखि A not B equals to A not C मा हामीले A इन्भर्स ले अपरेट गर्यौं कुन साइडमा, लेफ्ट साइडमा अपरेट गरेर यो प्रुफ गर्यौं भने B not A equals to C not A प्रुफ गर्नको लागि हामीले A इन्भर्स ले नै अपरेट गर्नुपर्छ, तर कुन साइडमा, राइट साइडमा. यदि यसलाई प्रुफ गर्नु छ भने हामीले के गर्नुपर्छ भने नाउ अपरेटिङ बोथ साइड्स बाइ A इन्भर्स अन राइट साइड, अन राइट. अपरेटिङ A इन्भर्स अन बोथ साइड्स बाइ राइट साइड तिर चाहिँ A इन्भर्सले हामीले के गर्नुपर्छ, अपरेट गर्नुपर्छ. सुरुमा चाहिँ हामीले A इन्भर्सले कता अपरेट गर्नु, लेफ्ट तिर, किनकि हाम्रो A चाहिँ लेफ्टमा छ. तर त्यहाँ चाहिँ ए कहाँ छ राइट साइडमा छ त्यही भएर हामीले ए इन्भर्सले चाहिँ राइट साइडतिर अपडेट गर्नुपर्छ दिस इज द प्रुफ अफ क्यान्सलेसन ल थियोरम 4 इन इलिमेन्टरी प्रपर्टिज अफ ग्रुपमा हामी थियोरम 4 मा छौं वी आर इन थियोरम 4 थियोरम 4 states that if a comma b belongs to g comma not then first we need to prove inverse of a not b equals to b inverse not a inverse and second we need to prove inverse of a inverse equals to a inverse of a inverse equals to a or double inverse of a equals to a now we go in first proof first we need to prove a not b whole inverse equals to b inverse not a inverse this we have to prove let ab belongs to g not therefore what we can say here a not a inverse equals to a inverse not a equals to e a not a inverse equals to a inverse not a equals to e we can say this because it's the properties of inverse element now we need to prove a not b whole inverse equals to b inverse not a inverse अब हामी यहाँ के गर्छौं भने b inverse not a inverse लाई a not b ले अपडेट गर्छौं a not b ले b inverse not a inverse लाई हामी a not b ले अपडेट गर्छौं a not b अपरेटिङ बाइ a not b यो चाहिँ किन गरेको भने हामीले b inverse not a inverse लाई a not b ले अपडेट गर्दाखेरि हाम्रो e आइडेन्टिटी एलिमेन्ट आयो भने हामी a not b लाई यसको इन्भर्स भन्न सक्छौं a not b लाई इन्भर्स अफ दिस भन्न सक्छौं अनि a not b को इन्भर्स त a not b इन्भर्स हो त्यही भएर b इन्भर्स not a इन्भर्स लाई हामी लेफ्ट साइड तिरबाट a not b ले अपडेट गर्छौं this we need to start from this we need to start equals to a not b inverse not a inverse this is associative law a not as it is b not b inverse not a inverse as it is associative law now b not b inverse equals to e b not b inverse equals to e a not e not a inverse since b not b inverse equals to e now a not e is a not e is a not a inverse since a not e equals to a and a not a inverse equals to e a not a inverse equals to e a not a inverse equals to e therefore a not b inverse of a not inverse of b inverse not a inverse is a not b or inverse of a not b is b inverse not a inverse therefore what we can write therefore I'll write conclusion here therefore the inverse of b inverse not a inverse is a not b that is b inverse not a inverse equals to a not b whole inverse similarly we can say that the inverse of a not b is b inverse not a inverse therefore a not b whole inverse equals to b inverse not a inverse therefore what we can say a not b inverse equals to b inverse not a inverse for all ab belongs to g this is the proof of this theorem it is proved this is the proof of this theorem it is proved now in the same theorem we prove 2 number double I we need to prove a inverse whole inverse equals to a let a belongs to g and a inverse belongs to g such that a not a inverse equals to a inverse not a equals to e now a inverse not a equals to e this we have a inverse not a equals to e अब यसलाई चाहिँ हामी के गर्छौं भने ए इन्भर्सको होल इन्भर्सले यो दुवैतिर मल्टिप्लाई गर्छौँ, ए इन्भर्सको होल इन्भर्सले दुवैतिर के गर्छौँ अपरेट गर्छौँ. नाउ operating both sides by A inverse whole inverse on left. किन लेफ्टतिर अपरेट गर्ने? किनकि यहाँ ए इन्भर्स छ नि त, ए इन्भर्सको होल इन्भर्स र ए इन्भर्स अपरेट गर्दा त ई हुन्छ, त्यही भएर लेफ्टतिरबाट ए इन्भर्सको होल इन्भर्सले अपरेट गर्नु पर्यो. सपोज ए नट ए इन्भर्स इक्वल्स टु ई लिने हो भने पनि अपरेटिङ बोथ साइड्स बाई ए इन्भर्स होल इन्भर्स अन राइट गर्नु पर्यो. फेरि ए नट ए इन्भर्स लिँदा चाहिँ ए इन्भर्सको होल इन्भर्सले राइटतिरबाट अपरेट गर्नु पर्यो, ए इन्भर्स नट ए लिँदाखेरि चाहिँ ए इन्भर्सको होल इन्भर्सले लेफ्टतिरबाट अपरेट गर्नु पर्यो. नाउ अपरेटिङ बोथ साइड्स बाई इन्भर्स अफ ए इन्भर्स अन लेफ्ट or A inverse whole inverse operating with A inverse not A equals to A inverse whole inverse operating E, or here we use associative law. A inverse whole inverse not A inverse not A equals to A inverse whole inverse not E equals to, we can say, A inverse whole inverse. Here we used two properties. One is associative law, another is E's identity limit. Since associative law and E's identity element, or A inverse whole inverse not A inverse is E, because inverse of A inverse element if A inverse whole inverse, this is E. E not A equals to A inverse whole inverse. Since A inverse whole inverse not A inverse equals to E, now E not A is A, therefore A equals to A inverse whole inverse. Therefore A equals to A inverse whole inverse. It is proved. This is the proof of this theorem. This is the proof of this theorem. Now we are in theorem 5 in elementary properties of group. If A comma B belongs to G comma not, then A not X equals to B and X not A equals to B have unique solutions in G comma not. These two are the group equations, and these two group equations, they have unique solutions in G not. We need to prove that. This proof. Let A belongs to G and A inverse belongs to G not, A inverse belongs to G not, be the inverse element of A, inverse element of A. Therefore A not A inverse equals to A inverse not A equals to E belongs to G. Now what is given is, now A not X equals to B is given, A not X equals to B. Now we need to operate here, we need to operate both sides by A inverse. We need to operate both sides by A inverse in left or right, in left, because A is here in left, A कहाँ छ लेफ्टमा छ. यदि मैले X not A लेको भएपछि म A इन्भर्सले कतातिर अपरेट गर्थे, राइटतिर अपरेट गर्थे, राइटतिर. यहाँ चाहिँ मैले A not X लेको हुनाले म A इन्भर्सले लेफ्टतिर अपरेट गर्छु. नाउ operating both sides by A inverse on left. Therefore, or A inverse not A not X equals to A inverse not B, or A inverse not A not X equals to A inverse not B. We used here associative property, associative law. Since associative law, now A inverse not A means E, or E not X equals to A inverse not B. E not X is X, therefore X equals to A inverse not B. Since E is an identity element, x equals to A inverse not B. Therefore, x equals to A inverse not B, which is the required solution, which is the required solution. This is the required solution. X equals to A inverse B is the required solution. Now we have to show that this solution is unique. We have to show that this solution is unique. Again, to show the solutions are unique, we suppose x1 and x2 are two solutions in Z. Therefore, what we can write is A0 x1 equals to A0 x2. A0 x1 equals to A0 x2, because A0 x1 equals to also B and A0 x2 also equals to B. A0 x1 equals to A0 x2. Now we need to remove this A from here. How to remove this A from here? A is here in left side, so we need to operate both sides by A inverse on left. Now, operating both sides by A inverse on left, or A inverse not A0 x1 equals to A inverse not A0 x2, or A inverse not A not x1 equals to A inverse not A not x2. This is associative law. We used it, associative law. Now, A inverse not A and A inverse not A is E. This is E. E not x1 equals to E not x2. Therefore, x1 equals to x2. Since E is the identity element. We supposed x1 and x2 are two solutions in Z, and we got x1 equals to x2. So therefore, there is unique solution in A0 x equals to B, that is x equals to A inverse not B. Similarly, we can show that there is unique solution in x not A equals to B. It is the proof of this theorem. This is proved. This is the proof of this theorem. It is proved.